Okay, questions on the homework? 4.10. What? 22?
23.
What did it say?
Let's do the multiplication by the matrix A. Find the first one is the basis of the range of T.
Okay, so basically T is, T of X just means multiplication by matrix A, and find basis,
We find four things. The first one is the basis.
the range,
The basis is the kernel.
basis for kernel, yeah.
The rank and nullity of T.
Rank T, nullity T,
And the same thing with rank and nullity of T. And B is a zero matrix.
where A is,
This matrix with columns of 1, 5, 7, negative 1, 6, 4, 3, negative 4, 2.
okay, so, essentially, based on what we've been doing, we're just looking at the same old thing that we've been looking at the whole time, but in a different context. All you have to remember is that what these translate to. What's the basis for the range translate to?
The column space.
Space in the column space of A. That's what they're asking for. And the basis for the kernel will be?
The null space.
So basically the null space of A is what they're asking for. And these, exactly the same. Right?
Why is the range, why is the column space the basis for the range?
The column tells you the inputs, right?
Right.
So you're talking about what space do the input vectors map to, where they go,
Okay.
right? So you're talking about, so if you have your guys here in the domain, right? And here is your codomain. Now those guys are going to, all of the guys in this set will map to some guys in this set, right?
Right.
So basically the range is determined by what these guys are doing. But these guys are coming from the columns. Right? So based on, if you figure out what's happening to the columns, like what space they span, then you're pretty much figuring out what's over here. Yeah, so that's basically it. So now, how do we find these? We find the reducer echelon form, or row echelon form is fine. So what would I do here?
Negative 5 times the first row plus the second one.
Okay, so you do row 2 minus 5, row 1. Okay, so this minus 5, this plus 5, right?
Yeah.
Minus 4, minus 15. Okay, and
Row 3 minus 7.
row 3 minus 7, row 1. So 0, this plus 7, and this minus 21, minus 19. So then you have 1 minus 1, 3, 0, 11, minus 19, and pretty much 0, 0, 0. It's just row 2 minus row 3. And so basically, the pivots will be here and here, and so basis for column space of A is the same as the basis for the range of T, which is just going to be equal to the column corresponding to the first column, 1, 5, 7, and the guy corresponding to the second column, minus 1, 6, 4. And so, and that's part A. Part B. How about basis for null?
Professor,
Yeah.
we have 11 there, or we can turn 11 to pivot.
Divide by 11.
Yeah, you just divide by 11.
Oh, okay.
It wouldn't make a difference. If you brought it here,
Yeah.
then you'd still see there's a pivot here and a pivot here. I'd still pick this and that.
Doesn't.
So it's less important of the actual value of the pivots than where they are. You need to know what columns or what rows they're in. So if you're looking for a row space, I just need to know what rows do the pivots appear in. And if I'm looking for column space, what columns do the pivots appear in. That's the importance for these guys. So basis for the null space, or well, the kernel is really just basis for the null space of the matrix. So basically, if we had this guy, 1, minus 1, 3, 0, 1, minus 19 over 11, 0, 0, 0. And it doesn't matter if I pick this or that. But if I augmented that with 0, and basically I want to find the guys with the parameters, right? So this is, say, call this x1, x2, x3. x3 would be my parameter. So the basis for this is only going to have one vector in it. And so x2 would be equal to 19 over 11t. x1 would be, that would be x2 minus 3x3. x2 I know is 19 over 11 t and 3t. And this becomes what, 33 over 11. So what do we have here? 19 minus 33.
14?
Okay. Yeah, this far I forgot how to add.
Yeah.
This reminds me of one of those comics. It's like, no, I don't remember doing that. Yeah, so now we have the x1, x2, x3 would be basically t times minus 14 over 11, 19 over 11,
1.
and 1. And so now, the basis for the kernel is just the set containing that one vector. Okay, so that was part B. Part C asks for what? The rank. Well, we know that since the dimensions of the kernel is 1, because there's one basis vector there, that means the nullity of t is 1. And this means the rank of t is equal to 3 minus 1. This is the number of columns. And this is the null with t. Right, using the dimension theorem, so the rank is 2. Right? Remember, when you add the nullity and the rank, you should get the number of columns, which is the dimensions of your input space. And part D is exactly the same. There's no difference between the two. Other questions?
21.
He says exactly the same.
Huh? What do you say? D, yeah, D's the same. I'm trying to confuse you with the words. Don't be confused. It's the same thing. Like the properties of your functions, you can get it directly from the properties of your matrix. That's something nice about linear transformations. You know about the matrix, you know about the function. So 21, what did that say?
Determine whether multiplication by A is a one-to-one matrix transformation. And A is equal to column 1 would be 1, 2, 3, and column 2 has negative 1, 0, and negative 4.
Negative 4? Okay. So find the reducer echelon form. So we have 1 minus 1, 2, 0, 3 minus 4, 1 minus 1. Here I can take, say, row 2 minus 2 row 1. Just minus that would be 0. 0 minus 2 times that would be 2. And then here I can take row 3 minus 3 row 1. That would be 0. 4 plus 3 is minus 1. So basically this is going to reproduce to that, right? So I can just double this and add it to that, kill it, and then I get a row of zeros, and then I divide by 1 to get that. So here, I know that the rank of A is 2.
There's also a part B.
Okay.
So A is equal to row 1 would be 1, 2.
Oh, a different matrix.
Yeah.
Yeah, but we haven't finished answering this yet. Remember, we want to tell if it's 1 to 1.
It's okay. Go ahead. Come on.
Okay. So what does it mean for the rank of A to be 2? Huh?
The number of dimensions.
This means nullity is 0,
The dimension is
Kernel is
right? In other words, the kernel
then it's
of this transformation has only the 0 vector. And we had a theorem that says when that happens, t is 1 to 1. Right? So basically you find the nullity or the kernel, one way in which you can do it. We had that theorem where these are all equivalent. Once we find any one, they're all the same. Not everything will apply, of course, because sometimes in that theorem we had A inverse and there are things about determinant. But obviously if we don't have a square matrix, we can't even talk about that. So we use something that we can apply to row reduction. We can use row reduction to solve for the homogeneous system. And if the homogeneous system only has that one solution, we also have that T is 1 to 1. Right, and it'll be the same concept for the other matrix. So actually find what the solution to the homogeneous system would be, and if it has only the unique solution of this trivial solution, then it's 1 to 1. If you get something like where you have parameters or something, it'll be not 1 to 1. What was the A?
The the first row would be column 1. So it's 1, 2, 3.
Oh, 1, 2, 3 this way?
Yeah, and then it's the same.
Oh, it's just the transpose.
Oh. Right, so right away you can tell this is not 1 to 1. Right? Based on a homework problem that we answered last time about the size of this guy, this is a 2 by 3. And so we know that the rank is at most 2, right? Which means the nullity is at least 1, which means infinite solutions. To AX equals 0. Right? Because I have a pivot here, which means this column I get a parameter for. Once I get a parameter, it's not a unique solution anymore. Right? Best case scenario is I have 2 pivots. Right? I can't have more. So I'll always have like a parameter here, which means I don't get a unique solution and the theorem breaks down. Other questions? All right, you guys have homework, so? So since we're talking about linear transformations, we'd actually continue with chapter 8 instead. You realize a lot of things are really familiar. A lot of it is just a change of vocabulary. It's not. Yeah, like pretty much through 8.1 to 8.3, we're going to see like maybe 2 new things really that are really new. So we're just going to be talking about general linear transformations. So last time we were talking about matrix transformations where we can think of the linear transformation in terms of matrices. Here we're sort of thinking of them as functions in general, although a lot of the time you will be able to condense them down to matrices. But so a lot of this is just rephrasing what we've done before. It's just how our book likes to do it. If I had more time before I was teaching this class and got the book, I would have rearranged. Sometimes I don't really get what they're doing. But this is like the 3rd time we're hearing about linear transformations, and every time they present is as if, hey, it's kind of different. It's exactly the same thing. Exactly. They mentioned in chapter 1, they mentioned in chapter 4, they mentioned in chapter 8. It's all the same thing. Why don't you just do it once and do it properly? You know? Oh, here's the linear transformation again. Oh, here's the linear transformation. Oh, it's a matrix transformation. Ooh. It's all the same thing. Okay, so this is a matrix transformation. If basically you can define your function to be multiplication by a matrix A, where A n by n is a matrix. So once you define a transformation in this way using a matrix and multiplying by some vector in a vector space, you get what we call a matrix transformation. One thing you should remember that matrix transformations are linear transformations. I guess you can think of this chapter as like a nice summary of what we've been doing so far. Linear transformations. And of course, you have to recall what a linear transformation is. So t from b to w be a function. B, w are vector spaces. Then T is called a linear transformation. If A T of x plus y is equal to T of x plus T of y, all x, y, a, b. It's called additive property. And b, t of kx plus k and kx, or k is scalar. They call this the homogeneity property. In higher math classes where we're talking about functions between different kinds of sets, they don't have to be vector spaces. You can have this sort of setup between things called groups or rings or fields. modules, lots of different things, and they all have different names, but they're basically the same thing. Like in general, what you'd call a linear transformation for vector spaces, you'd call a homomorphism for general things. So if you see that word later, just think of this, it's the same thing. New terminology, if V is actually the same as W, then T is called a linear operator. I probably told you that already, it's all a blur at this point. I guess the good thing is now you'll remember it since we're repeating it so many times. An important property, we've used this before, but it's really the first time I'm kind of formally introducing it. We can combine these properties to get something like, if I take T of C1 V1 plus C2 V2, then I can write this as C1 times T of V1 plus C2 times T of V2. You just apply the additive property first, then the homogeneity property second, and you can split things up. One thing they want us to realize here, or to take note of, is that you can continue this for any finite number of terms. You can use induction to see that C1 V1 plus C2 V2. And I have n of these terms, C and Vn. Then that is equal to C1 T V1 plus C2 T V2. They also mentioned a theorem which, incidentally, we actually kind of proved this last time. Well, maybe not the first one. We used it. But T from V to W be a linear transformation, then the following two properties hold. T of the zero vector is always the zero vector. A linear transformation will always map 0 to 0. And it doesn't matter if you use subtraction instead of addition, that will distribute as well. Your book uses the homogeneity property to prove this, but I'll use the addition property. Notice that T of the zero vector is the same as T of 0 plus T of 0 plus 0. That's true. And so now I can use the additive property to split it. And so this means T of 0 equals 0 by definition of 0 in a vector space. Because it's the guy that when you add to someone, you get himself. That's proof of A. Proof of B. T of x minus y is equal to T of x plus minus 1 times y. We proved that these were the same for vector spaces. Now we can use the additive property. And now we can use the homogeneity property. This is the scalar k. I can just factor it out in front. And since ty lives in a vector space, minus 1 times that is just the negative. that's no surprise there. 0 goes to 0, negatives we can also distribute across negatives. This is true in a vector space in general, and it is true here. By the way, I should probably note that just a helpful conceptual thing. So if we know that T goes from V to W, and V, W are vector spaces, then for T of X, both X and T of X are elements in a vector space. Meaning everything you know about vector space, you can apply those concepts to these two elements, right? The vector that's in here, as well as its output itself, you can treat them just like vectors. Any properties that work for vectors will work for them, because X will live in here, which means it's an element of a vector space, and T of X will live in here, which is an element of a vector space. So anything that works with vector space, you can do it with these guys. Right? So I can use any of my vector space axioms, or any of the properties I prove with vector space, like -1 times something is the negative of the thing. We can use all that here, because they're really vector spaces. So if you're ever trying to do a proof or something, you can't really see what to do, you can sometimes think of it as a vector space and see if thinking of it that way can help you figure something out. We give some examples of operators here. We've used some before, but just to do some ideas. There's the identity operator, right, which is kind of like a multi-dimensional identity function. That's the guy that says T of X is just IN times X, right, which just gives you X again, right, where N is the dimensions. Another example. Differentiation is a linear operator. So I can think of as T as going from Pn to Pn, which we know are vector spaces, and I can define that as T, P, some vector there, is just P prime, the derivative. And T of P of X is just P prime of X. That will be linear. We know that derivative distributes across sums, and we can factor constants out when we're doing derivatives. So that's an example of a linear transformation. And it's called an operator when the output and input spaces are the same, domain and range. Let's say T goes from N, and I defined T of a vector to be its transpose. That is a linear operator. Right? We know about the properties of transpose, distributes across sums, and you can actually factor scalars out. Also, if T is defined to be multiplication by A, then we can then for t, I feel like I've gone from fn to fm. We can think of it as the following. Basically, we're transforming the basis vectors. That's a very important idea. Yeah, so you can think of this as a change of basis. For the standard basis vectors on F. And this idea we can kind of use in general. So for example, when we were doing in 4.9, we didn't really talk about it, but we should have tried the problems. You think of something like t of a of x, just another example, being ax, where we wanted a to be rotation matrix of theta, right? And so if you wanted to say, go from R2 to R2, what was the standard rotation matrix for this?
Theta minus sine theta, sine theta,
Which, where?
cosine theta, second minus sine, sine theta, cosine theta.
So say you forgot that. You can sort of use this idea to reconstruct it. All you have to do is figure out what happens to your basis vectors for the operation you want to happen, right? So I can, if I'm in R2, the standard basis vectors will be I and j, right? So it's 1, 0, and 0, 1. So then you start to think individually, what would happen to I and j if I rotate by theta, right? So here's my I vector, right here from 0 to 1. Now if I rotate that by an angle theta, right, where theta is this angle, what is going to be the new coordinates of this vector? Well, it's going to be cosine theta, sine theta, right? So in this case, I can think of the transformation of the I vector as the vector cosine theta, sine theta, right? So I know that my I column of A will be that vector. And then I do the same thing for the j, right? If I try to figure out what would happen to j if I rotate by, right? So here's my j vector. Now I rotate that by an angle theta to get this vector. What will be the coordinates of that vector? Well, you sort of turn the triangle, the right triangle on its side. You use SOHCAHTOA. The opposite now would be the sine, right? But that is actually the x coordinate, and I also know it's negative. So the x value would actually be the negative of sine theta, right? Whereas the y coordinate would now be this, which is the cosine, right? So this would be the cosine theta. And so I know that the transformation of the j vector would be the vector minus sine cosine, right? And so now, together, these imply that my A is just the transformation of I, the transformation of j. And so you get cosine theta, sine theta, minus sine theta, cosine theta. Right? So if you want to figure out some sort of operation, if something you want to do to a vector that's a linear operation, which means it's a scaling, a rotation, a reflection, a dilation, or a contraction, or a shear. Those are all the linear transformations, right? If you do something else, it's not a linear transformation anymore. But yeah, you can actually figure it out. All you have to do is figure out what happens to I and j when I do this, and you can literally build up the columns of your transformation matrix that way. So once you figure out what happens to your original standard basis vectors, you know what happens to everyone. You just throw those guys in a matrix, and it's pretty much 4.6 all over here. A lot of things are 4.6. It's a very important topic section. We spent a lot more time on 4.6 than I wanted to, but in retrospect, I'm actually happy we did. A lot of things come back to 4.6. What do you want to say? Okay, something else. T from V to W. Assume that's a linear transformation. And V is in V with, let me define the basis for V first. V equals V1 up to Vn is a basis for V. What does it mean to be a basis? Linear independent, and it spans the set. What does it mean to be linearly independent?
Can express linear combination.
Should I that as
Evan should be telling me this. It's really a question directly at Evan. I notice how he's quiet over there. He's just chuckling. Okay. Then V we can write as we know C1 V1 plus C2 V2 plus da 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 Cn Vn for V in V. And this also means that when we're in our output space, when we're in the codomain, we can also express our output vectors in the same way. So then T of V, if I look at in the codomain, that would actually be T of C1 V1 over to Cn Vn, and this would be so basically, there are many things you can get from this. For example, one, if you know that T is onto, then the transformation of your basis vectors is also a basis in the new space, things like that. You also see here that in these guys live in the range. You'll notice that the space spanned in the range is determined uniquely by the basis vectors from the input, right? Which is kind of why the basis for the range is actually the column space, right? Because once you know what happens to those columns, which are the input guys, you know what happens in the range, right? Because it's just a transformation of the input guys. So that's why we know that when we're looking for a basis for the range, we're actually looking at the column space of A. Because it's our input guys that will carry over to the output guys, and we can sort of write them in a linear transformation, a linear combination in exactly the same way, using exactly the same coefficient. We also know the following. T from V to W is linear. A. The kernel of T is a subspace of V. The range of T is a subspace of W. So which means these are vector spaces in their own right. In fact, their basis vectors are the transformations of the basis vectors from the input. C. If R of T is finite dimensional. Then the rank of T is actually equal to the dimensions of R of T. D. If kernel of T is finite dimensional, then the nullity of T is just the dimensions of the kernel. We also have a dimension theorem here, which is the same old dimension theorem, just stated differently as if it's something different, but it's not. Okay, the rank of T plus the nullity of T. You get the dimensions of V, which, by the way, V is your domain, which is the input, which is the number of columns. The dimensions of V would be the number of columns you have. It's exactly the same as the previous dimension theorem, just stated in a different language. That's kind of 8.1. It's very conceptual, not many calculations in these sections. 8.4 is calculation intensive. We'll actually do that after the break. I think that'll be good for you guys to see for your final. This talks about composition and inverses. And yes, all your intuition for matrices apply. Composition is really just multiplying two matrices. Here, recall the definition of one-to-one and onto. I'm not going to write it down again, just make sure you remember that. Moving on, here's a theorem that works in general. So T from V to W is a linear transformation. Then the following are equivalent. Everything's that are equivalent. A, T is 1-to-1. B, the kernel of T is actually 0. Right? We use this fact in the homework. It's officially stated in 8.2, even though we already knew it in a different language. Right? But notice that we had a larger theorem earlier, but that's because we were assuming that our matrices was going from Fn to Fn, which means we had a square matrix, so we had determinants and inverses and all that. But in general, you won't have that if your dimensions of V and W are actually different. But these two will hold true, no matter how your dimensions are respectively. So I will note that. Dimension of V is not necessarily equal dimension W. If dimension of V equals dimension of W, in that case, we also have that T is on T. But in general, you won't have that. In general, though, you will have these two being equivalent. If your dimensions actually match up in both the vector spaces, then you'll also get onto for free, which means you automatically get invertibility. So, what else do I want to say? Call again. T1 goes from U to V, T2 goes from V to W, linear. And these are the definitions. T2 composed with T1 of X is just T to T1 of X, which you might call T21 of X for short. If your T1 is equal to just A times X, your T2 is equal to B times X. Then the composition is just a multiplication of these two, which I think was one of your homework problems, though no one asked about it. So in that case, T2 composed with T1 is really just TB composed with TA. Turns out that would be TA, which is actually the matrix B times the matrix A times X. And if T2, T1 are linear, then so is their composition. To compose two linear transformations, the result is also a linear transformation. The proof is not hard. I could ask that in the test. Also, if they're both 1-to-1, then their composition is 1-to-1. Also, if T2, T1 are invertible, which means we're thinking of them as going from vector spaces that have all the same dimensions, and you can actually reverse them, then take T2 composed with T1, you take the inverse of that. Guess what it is? The inverse in the opposite order, because matrices behave that way. That's kind of 8.2. So basically regurgitate what we knew and eating it again. It's kind of what's going on. There's nothing. Yeah, well, the homeworks here I would assume are more proof-based, right? They really want to make sure you guys are used to the ideas of these things, rather than being very computationally intensive. 8.4 will be computationally intensive, and we'll actually do that. 8.3, isomorphisms. Definition. It's not a big deal. It's basically an invertible linear transformation. We call it isomorphism. T goes from V to W, a linear transformation. If T is 1-to-1 and onto, then T is called an isomorphism. An invertible linear transformation, the technical term is isomorphism. FYI. What's that word that tells you about where the origin of a word comes from? Etymology.
Etymology?
Logically. Isomorphism means same form. So that brings us here. If T from B to W is an isomorphism, then B and W are called isomorphic. So you'd say like V is isomorphic to W. And based on what the word actually means, you can see where we're going with this. They have the same form as vector spaces. And B as vector spaces they are mathematically indistinguishable. Now that's a super useful property because it means that if I know about one vector space and I know it's isomorphic to something else, knowing everything about this is the same as knowing everything about that. There's literally no difference. The elements, sure, the elements might look different, but really, mathematically, there is no difference between the two. Solutions to equations in here will be exactly the same to the corresponding solutions to the equations in there, and so on and so forth. There will be no difference at all. It's more like, over here you have normal people, over here you have the same people who witness protection. We just change all the names to protect identities, but it's really the same people walking around, and we can't actually tell the difference between them. No, it's 350. That's not good. I just have more phrases to identify. There's no more meat really. So you can try the homework for 8.1 and 2 and prepare for the test, which is when you come back from the break.
Would the homework be due on the daily test?
Huh? It's the test is the Monday when we come back. The homework, you can bring it in Wednesday. It's on the fine tune.